Okay, so we're now going to be looking at the product rule for multi-stage events, and this will relate to exercise 10E from the textbook. So what the rule basically says, if we have a multi-stage experiment and A and B are events, and our rule actually goes all the way down to Z, so there's all independent events A, B, C and D, and they're happening at different stages, one stage doesn't affect another. So the probability of A, B and C occurring would be the probability of A times the probability of B times the probability of C. So each event is independent or not affected by the other events that are happening. So I've just jumped over to the next page of the OneNote 10E, multi-stage events, and that's where I'm going to work through the information that you can write onto your sheet. So a simpler way of writing it, we would say the probability of AB is equal to the probability of A times the probability of B if those events are independent of one another. A good example of that is throwing a dice and then tossing a coin. They don't have anything to do with each other, and so we can work out the probability of the information required for the dice and multiply that by the probability of the information required for the coin. And we could use that theory in this first example about tossing a coin. So a coin is tossed 5 times. We want to find the probability that every toss is a head. Now we could draw a tree diagram for that, and that would be a rather large tree diagram, but if we think of it as that's the probability of getting a head, a head, a head, a head, a head. So 5 heads thrown in a row. Each one of those tosses is really independent of each and every other toss. So each toss itself would be a half. Because we have a head of it or a tail, we've got a half. We've multiplied that together, 5 times, and we're going to end up with 1 out of 32. So if we think of it like that, we're not needing to draw that tree diagram, but if you needed to, you would just end up with 5 specific columns in that tree diagram, and it would be quite large. We could use that to find the part B. Find the probability that no toss is a head. So if no toss is a head, then we're basically getting 5 tails. So it's the probability of, and I've written 5T there for 5 tails, but it's the same as getting a tail, a tail, a tail, a tail, and a tail. So 5 tails. So our answer is going to be the same as the first one. We're going to have a half multiplied together 5 times. So we're going to get 1 over 32. The third part of that question, part C, says, find the probability that there is at least 1 head. So the probability that there's at least 1 head is written. It's written like this. So the probability of at least 1 head is equal to 1 minus the probability of no heads. Okay, so we think about, we looked at this the other lesson. So no heads and at least 1 head are going to be equal to 1 whole. Okay, so no heads means 5 tails. Okay, so the probability of at least 1 head is 1 minus the probability of 5 tails. We've worked out 5 tails being 1 over 32. And so that's going to be 31 over 32. Okay, let's have a look at the next example in there. It says a box contains 5 discs numbered 1, 2, 3, 4, and 5. 2 numbers are drawn in succession without replacement. What is the probability that both are even? So that's asking us to find the probability of an even number and then an even number. So let's use the rule for that. Okay, so we're using our 2-stage experiment rule that's saying the probability of AB is the probability of A times the probability of B. If we go back to our question, we want to find then the probability of an even number and then a probability of another even number. But the key thing here is without replacing it. So let's look at the first number that we pull out. Okay, so let's look at what happens to start with. There's 5 numbers, and of those numbers, 2 of them are even. So 2 and 4 are even. So the probability of choosing an even number to start with is 2 out of 5. Now, what we're going to assume to get our second fraction is that we've pulled out an even number. Okay, so we have 4 discs left in the box. We've removed one of the even numbers. So we've only got one of those even numbers left. So we've got 2/5 times a quarter. We're timesing those together, that breaks down to 2 over 20 and then 1 over 10. So that's the probability of an even number and an even number. Now, you also could have done that with a tree diagram, and I've done that, but it's actually going to take a lot longer. But if you can't work it out the other way, you've also got that option. So here's what it would look like. Here's our box. Our numbers are 1, 2, 3, 4, and 5 for our first number. And our second number, it says without replacement. Okay, so we're not putting the number that we've picked out back in. So our second number is only going to have an option of 4. So if we've picked a 1 to start with, our second number for the 1 can only be 2, 3, 4, or 5. We go down, say for example, if we picked a 4, our second number can't include a 4, it could only be 1, 2, 3, and 5. And that's going to make it the case for each one of those. I've written a sample space to the side, so that just shows me moving along that tree. I'd have a 1 and a 2, a 1 and a 3, 1 and a 4, etc., all the way down to a 5 and a 4 and a 5 and a 5. So I've written our sample space down. So all up, if we count that up, we've got 20. That number 20 comes from having 5 choices to start with and 4 in the next part of our tree. So 5 times 4 is 20, or you can add that up. And we're looking at the probability of an even number and an even number. So if I go through there and look down, I've ticked the only options. There's a 2 and a 4 that give us 2 even numbers. A 4 and a 2, we can't have any in 1s or 3s or 5s because those are odd numbers. So an even and an even, there's 2 options out of 20, which we got over here. And we break that down to be 1 over 10. So we get the same answer, but that gives you 2 options to do that question. There's another example here that is in the OneNote that talks about sending out some Christmas cards. The solution for that one is the OneNote. The next one is quick quiz 3. 6 girls' names and 5 boys' names are placed in a hat. 2 names are drawn without replacement. What is the probability that a girl's name and a boy's name are chosen? Okay, so that will mean we will have 11 names in total in the hat. So that means we can work out our probabilities. So we're looking at a girl's name and a boy's name being chosen. We're trying to find out the probability of a girl's name and then a boy's name. They're independent events, so we can write the probability of a girl's name being chosen times the probability of a boy's name being chosen. Okay, so the probability of picking a girl's name would be 6 out of a total of 11. Now what the question says, if we have a look back through that again, it said 2 names are chosen without replacement. So if we've already picked 1 card out and it's a girl's, to get the probability of the boys, we're only choosing out of 10 because we don't have 11 in there anymore. And they're independent, so the fact that we've chosen a girl's name won't affect the fact that we need to choose a boy's name. So our second number there for probability of choosing a boy's name would be 5 out of 10. Multiplying those 2 fractions, we get 30 over 110, which breaks down to be 3 over 11. So the probability that a girl's name and a boy's name are chosen is 3 out of 11.